Okay, so it turns out that there is a way to get rid of back propagation, and there is no need to like calculate that explicit f dash in the error signal. And the way you can do it is like this. So let's say that for a moment you are looking at the last layer of a network. So let's say that you are looking at a last layer of the neural network, and that neuron is basically the neuron I, and it's connected to the neuron J, which is the layer just before it. Okay, and now your neuron is obviously going to output some activity yi, and let's say like you have a target T. Okay, so in this case I am assuming like that the neuron activation is linear. So like for the neuron I, like whatever input goes in is whatever output comes out, and then the loss is basically given by the MSE loss. So this is like a standard setup, a standard regression setup, where a lot of people use like the quadratic loss and quadratic like difference, and then this is like a mean square loss, and this is like pretty cool because the gradients appear to be very nice. So what happens is that if you take like the derivative of this loss with respect to like the outgoing activity, the twos cancel out, and you are left with like just the difference between the output yi which you predicted and the network's true output, which is T, and this is like known as delta y. Okay, so you can imagine like the first phase of this algorithm is that you feed in like your input, and then you get this xi that this predicts yi, and then you compute like the error between the yi and target, which is like just a normal L1 loss, and then that gives you like the delta yi. So now the key point is that you can actually use like this difference in the activity, so this difference in the activation pattern in a very subtle way to get the gradient on this particular weight wij, and you actually don't need to compute like f dash or any particular sort of secret sauce or like any sort of complex expression, and there is a way to get around it. So this is like the first phase of our algorithm. So now let's assume that so you fed in like xi, you got yi, and then you got like the you had like a target, and then you calculated the difference between them, which we called as like epsilon, right? So in this case like epsilon was like in this case epsilon is like del L by del yi. So you can see here that when you take the derivative of loss with respect to like yi, it comes out to be delta y, which is the difference in the activity, and we call this particular term del L by del yi to be like epsilon. And this epsilon is nothing but the difference in the activity which the neurons outputted. And the reason that this is like a difference in the activity is because the neuron is linear, and you are using like a standard loss which is MSE, and this assumption only holds in that particular case. So let's say that you have like so you fed in input xi, you got yi, and then you computed this epsilon. So now the key idea is that you feed back this epsilon again to like the input xi. So what happens is that let's say you have a function f which you have xi and you got yi, and you computed this epsilon. Now the idea is that you feed back this epsilon as input. So you can see that f of xi plus epsilon can be written as f of xi plus epsilon times f dash xi. And if you take in this case like the difference between the output, now the difference between the output of the neuron, it comes out to be a very beautiful expression which is epsilon times f dash xi. And in this case like when we assumed that our when our output neuron was actually linear, so when this I was actually a linear neuron, and when you were taking the loss as just a MSE loss, then in that case the epsilon is basically del L by del yi. So now you can just plug in this expression, and you can see that it essentially gets this whole thing back. So you can see that if you fed like in the first phase you fed xi, you got yi, you computed this error e, and then you just added that error back to the input, and then you got like xi plus epsilon, and you passed it again as a simple feed forward through the same neuron I, which gave you like a activity y dash. So you remember the old yi and you remember the yi. So this y dash I minus yi actually gives you like it actually gives you like this particular error signal. So in this case you never computed f dash you never computed f dash. So the algorithm is like pretty simple, that okay, you have xi, you assume that your neuron is linear and it's using a MSE loss, you can compute like this yi, and then the difference from the target is basically yi plus epsilon, and you can compute like this xi plus epsilon, and you can add like this xi to the input, and then whatever output you will get, whatever change in output activity you will get, this new epsilon will be actually the error signal for that particular neuron. So then let's say this whole epsilon is basically like, let's say this epsilon is something, it's like the error signal, right? It's lambda. So then you can easily compute like the weight update which needs to be made to this neuron as like delta times multiplied by the input activity which is coming in, which in this case is like xij, and that would be the change which you need to make on the particular connection. So del L by del Wij is minus eta times xij times del, and you have already computed the error signal delta without actually having to differentiate y in the first place. So this clever idea in which like you can use like the activity difference of activity, in this case like you use this epsilon and you fed it back to the input, and then the final output activity which you had was actually the one which contained the gradient update you need to make. And the key point is you never had to compute f dash, and that's more biologically plausible. So in this case, like your I can be any model, it can be any functionality, you don't care, and then it can also change like as the network is learning even its own function. The very function it is modeling can change, but you can still train the damn thing because you don't need to know the precise mathematical formulation, and like essentially you have gotten rid of like this problem of backpropagation that you needed to know y equal to fx very precisely beforehand. Now everything is that you feed xi in, there is some neuron you don't know what it is, so it's just a black box, and then it gives you yi, you compute like with the target, you compute the error which is epsilon, and then you feed like this epsilon back to like this input neuron, and then whatever output you have, in this case y dash I. So in this case if you subtract like this y dash I from the input activity yi, you can get like the final gradient change, you can get the final error signal which you can use to update like this neuron's weights. So now you can see that this is a way in which you can get around, you don't have to compute like f dash in any way, but this type of processing still needs two things. It still requires xi to be stored in the memory, and it still requires yi to be stored in the memory. So like when you're computing this epsilon, to get this expression of xi plus epsilon, you cannot compute this without by just like you have to remember this xi somehow, and to do that like you need to actually store xi in the memory, and that is like a key problem still. So if you look at the limitations of backpropagation which we had earlier, we have solved this particular limitation in which that we need to know f dash, and actually you can get around it by just like funneling this difference of activity in the neuron back, and then it will give you like the error function, but we are still storing like xi and yi in the memory. And like these first two limitations are the limitations which we still haven't solved. So is there a way to solve this limitation, which is namely that you still have to store this xi in the memory to be able to do this second phase of the algorithm, in which like to be able to do this second phase of the algorithm where you were feeding xi plus epsilon, and you could not get this without storing xi in the memory first. So this whole proposal is really good because you can now pipe the gradients as a difference of activities, and you got around f dash, but you still need to store xi in the memory. So the next part is how do you actually overcome this requirement of having xi in the network, like how to just forget storing it anyways.